This is a presentation on the two types of nuclear power, highlighting how they work, the energy we can obtain from them, and a comparison of the two. The first is nuclear fission. It is a series of chain reactions that release large amounts of nuclear binding energy when a single nuclei breaks down into smaller nuclei. To start this chain reaction, a neutron is fired at the original uranium-235 atom. This extra neutron causes the nucleus to become unstable in the form of uranium-236. The nuclei then splits due to electromagnetic and strong force imbalance. When it decays, it separates into two or more smaller nuclei. In the nuclear fission reactor, neutrons are continuously fired at the unstable nuclei and the decayed products of the reaction. This diagram represents the nuclear binding energy released by varying mass numbers. In the case of fission, the binding energy, seen on the y-axis, is the energy released when the single nucleus separates. This process is described by Einstein's famous equation E = mc². The sum of the masses of the resulting nuclei and particles is slightly less than the mass of the original uranium nucleus. The mass lost is converted into energy according to Einstein's formula. As you can see, about 7.7 MeV is released per nucleon, but from a uranium atom about 210 MeV of energy is released. We find this value when we find the difference of the uranium mass number times the energy released per nucleon, and the combination of krypton and barium, giving us about 210 MeV. The main fuel of nuclear fission is uranium, otherwise known as yellow cake. There are three isotopes of uranium that can be found in the environment. These are uranium-234, 235, and 238. The percentage found in the environment is about 0.01%, 0.7%, and 99.3% respectively. However, fission requires uranium-235 as a fuel in the nuclear reactor. To get this, we must enrich uranium-238 using a method called gas diffusion. First, we mix uranium and fluorine to make hexafluorine, and we feed this into the reactor, where it's filtered by hundreds of barriers. The large hexafluorine molecules are too big to fit through the holes, and this breaks down into uranium-235. This is what a typical nuclear fission reactor looks like. The uranium-235 is put into the reactor core, and from the chain reaction we get thermal energy. This is used to heat water, turning it into steam. This is fed through to the turbine, which powers an electric generator. Power can then be distributed to buildings from here. There are two main mechanisms which are used to control nuclear fission. The first is the moderator. The point of this is to slow down the neutrons fed into the reactor core. The second mechanism is the control rods. They contain neutron-absorbing materials such as boron or cadmium. By absorbing the neutrons, it does not allow the chain reaction to continue. This diagram represents the countries already using nuclear fission. The darker areas represent high levels of fission production or consumption, and the lighter areas show the opposite. At the moment, there are about 438 nuclear fission reactors around the world. These reactors generate about 345,000 megawatts of electricity in 32 different countries. This is about 1/6 of the world's total supply of energy. Nuclear fission is one of the largest power constituents of many leading countries. For example, it is about 76% of France's power, 56% of Belgium's, 25% of the UK's, 33% of Japan's, and 36% of South Korea's. So, how much energy does nuclear fission produce? One atom of uranium produces about 210 MeV of energy. To put this into context, 60 kilograms of uranium has the energy equivalent of about 15 kilotons of TNT. In terms of electricity, 1 kilogram of fission contains about 2 or 3 million times the energy equivalent of coal or oil. For low-level waste, such as contaminated shoe covers, clothing, rags and filters, it is typically stored on-site by licensees, either until it has decayed away and then it can be disposed of as ordinary waste, or until amounts are large enough for shipment to sites with approved containers. For high-level waste, until a permanent disposal repository for spent nuclear fuel is built, licensees must safely store this fuel at their reactors. This type of waste must be stored and contained and buried underground, as it may take hundreds of thousands of years to decay, emitting harmful radiation. Although fission sounds like a great form of energy, there are some difficulties. First, the disposal of unwanted radioactive waste. Licensees must find uninhabited areas to dig and buy materials suitable to contain the waste. In addition, the byproducts, such as radioactivity, is very harmful to the environment when exposed. and can take hundreds of thousands of years to have decayed completely. Furthermore, if a nuclear meltdown were to occur, the radiation would be extremely hard to contain and may cause areas to become uninhabitable, as seen in Chernobyl. Finally, if we were to make fission our main source of energy, there would be global access to nuclear weapons, so ideally we would want a more safe and secure form of energy. Nuclear fission is the collision of two nuclei which release large amounts of energy when they fuse. The first step is to remove the electrons and outer layers to expose the nuclei for collisions. We do this using heat and electric fields causing the atoms to shed off their unwanted outer layers. This creates an ionized plasma. Since these two nuclei will be positively charged, we move the plasma at high speeds, causing small fractions of nuclei to stick together. When we do the atomic calculations to find MeVs produced, we find fusion produces about 18.3 MeVs per atom. Since fusion is between hydrogen atoms, if we fused enough hydrogen atoms to the mass of a single uranium atom, we would have a substantially higher energy output. The most common type of fusion reaction uses deuterium and tritium. The fusion of these create a helium atom, a neutron, and about 18.3 MeVs of energy. This means that there is about 3.66 MeVs per nucleon. To put this into context, if we were to burn 1 kilogram of fuel through fusion, we would obtain about 9 times 10 to the 16 joules of energy. This is about the same amount of energy as a megaton of TNT. With nuclear fusion, we are essentially recreating conditions similar to the Sun on Earth. On the right, the nuclear fusion reaction in the Sun is displayed, which again produces a helium atom, neutrons, and binding energy. To create fusion on Earth, we must make temperatures 10 times greater than that on the Sun, which is about 15 million degrees. Fusion is possible at lower temperatures on the Sun due to the high density levels, creating a huge problem as material in contact with the high levels of heat will be instantly melted. In order to start this process on Earth, we must first create ionized plasma, which we can do by passing through a voltage. Magnets confine charged plasma to an extremely small area within the reactor. This maximizes the chance that superheated ions will fuse together and give off energy. The heat generated turns water into steam, and this causes turbines to spin, like fusion, producing electricity which can then be distributed. So, to ensure collisions occur, and also that plasma does not come in contact with the reactor walls, the vessel is surrounded by huge electromagnets. This creates a magnetic field 10,000 times stronger than Earth's, and only allows plasma to circulate in a specific area of the reactor. To actually get plasma into the fusion reactor, we heat hydrogen gas until it turns into plasma. This is then squeezed into the reactor by superconducting magnets. This is the joint European torus at Culham, Oxfordshire. It's the largest magnet fusion device in the world and was constructed between 1978 and 1983 with a budget of about £500 million. It's about 3.1 meters high and is surrounded by 32 toroidal magnets and 6 poloidal magnets that work to create a huge magnetic field inside. In terms of extracting energy from the fusion reactor, we know that about 80% of the energy emitted is with the neutron and 20% is with the helium. Since the neutron is not charged, they fly out of the magnetic field cage inside the reactor. They are slowed down by a lithium blanket on the walls of the vessel. Thermal energy is converted to electrical energy, which is then able to be passed on. The lithium blanket also reacts with neutrons emitted to form tritium, which can be then fed back into the reactor. However, as good as this sounds, there are some difficulties with nuclear fusion. Fusion requires approximately a density of 1 mg per meter cubed and temperatures of plasma that must be between 100 and 200 million degrees Celsius. Therefore, if the reactor is not perfect and the plasma gets too close or touches the wall, then the plasma will burn straight through the wall and a new reactor must be made. This is risky and costly due to the large budget it requires to build a nuclear fusion reactor in the first place. The fuel of nuclear fusion are isotopes which can be extracted from seawater. This means we can fuel nuclear fusion with an abundant resource. Another advantage to nuclear fusion is that it creates short-lived radioactive waste, which quickly decays to background level radiation. In nuclear fusion, there is something called the triple fusion product. Physicists combine three parameters of temperature, density, and time. When we multiply these together, we get the triple fusion product. At certain values of this, the reactor becomes self-sustaining and the heat generated by the reaction is enough to keep the plasma hot, so the external heating systems can be turned off. So, which is better, fission or fusion? Fusion provides the most energy per kilogram than any form of energy we currently have. It requires an abundant and safe fuel, water. It produces less dangerous and generally less radioactive waste, and there is no possibility of a nuclear runaway. Fission produces less energy per kilogram and has radioactive waste that can last for thousands of years, and we must spend on reactors to enrich uranium-238 and also for the uranium-235 to produce energy. If we produce these everywhere, all countries would have access to nuclear weapons and fuel for them. In the current global situation of rapid depletion of natural resources and burning of fossil fuels, an alternative energy source, ideally environmentally friendly, is in high demand. Nuclear fusion is a major low-carbon energy source and is expected to grow substantially in the future. Fusion would be the most efficient and most environmentally friendly option. At the moment, its fuel is practically unlimited and does not pose many negative impacts on society. Until science produces a more efficient or more sun-reliant energy source, nuclear fusion would be the best option going forward, especially taking into account global warming.